Okay, the last thing that we need to do is talk about something that we talk about all the time in calculus, which is optimization of functions. So one of the things that we did a whole lot in Calc 1 is do things like find maxima and minima. And remember, when we were finding, oh geez. So remember when we were finding, let me make this full screen. We were finding maxima and minima, the whole thing was that our derivative, and of course I'm using this old notation because it made more sense when we were talking about single variable, was that the derivative equaled 0, and that was what gave us something called a critical point. So the same thing is going to happen in multivariable calculus, except it doesn't make sense to just do one derivative anymore. Now we need to find the partials. So instead of just saying the derivative of the function equals 0 at a critical point, we say both of the partial derivatives have to equal 0. That's what gives us a critical point. So a relative max or a relative min for a multivariable function. So let's just start with an example of that. So let's find all of the critical points of this two variable function. So the first thing that I'm going to do is find my partial derivative with respect to x. So in this case, my partial derivative with respect to x is just negative 2x, and my partial derivative with respect to y is 2y. And remember, everything else is treated as a constant. So I need for both of these to be 0. So this sort of gives me like a system of equations almost. We can think, well, negative 2x has to equal 0 and also 2y has to equal 0. It's a system because both of these things have to be true in order for us to have a critical point. So the only way for this to happen, the only way for both of these equations to be solved at the same time is if x equals 0 and also y equals 0. So putting those things together, the point 0, 0 on the plane is a critical point of this multivariable function. So there's our critical point. Now, of course, it doesn't tell us if it's a maximum or a minimum, but it does tell us that it's a candidate for those things. Then we'll have to come up with some other tests to determine whether it's a max or a min. And also, one thing is, let me just make sure this thing is still recording because I'm kind of very nervous about this now. One thing that we can point out is our main tool for doing that in single variable calculus was something called sign analysis. And we would like put our critical point here and then we would say like, okay, positive, negative, and that would tell us some stuff about our function. The problem is with that, once we're dealing with multivariable functions, we can't really use sign analysis because we have this whole other dimension going on. And it's also not enough to just check what's going on in two different directions, because we have all these other directions going on around this critical point. So like I don't really know what's going on over here or here or here or here or here or over here. So there's all these different places where I need to check. So sign analysis is just not quite so simple when we're talking about multiple variables now. So imagine, for example, that we have a function like this. And I've referenced this a few times in our lesson so far. I talked about it as being like a Pringle chip. So this is a function that has something called a saddle point. So you can kind of see, I'll try to make this show up in a different color. If you're walking along the function in this direction, you sort of walk over this hill and then over the other side. But if you're walking in this direction, you walk down the hill and up the other side. And in both cases, we're passing through this point, which would have some importance, especially along this yellow trajectory, because along this yellow path, you're walking up the hill and then you reach the top here. So if someone was walking up this yellow path, they might say, well, that blue star is a maximum. I reached a maximum point right here and then I walked over the other side, but the blue star was the maximum. And if someone was walking along the purple path, they would walk down this way to the bottom of the hill and then back up the other side, and they would have a completely different interpretation of this point. They would say, well, I walked down to the bottom and then up, so this blue star is a minimum. And that's what makes multivariable calculus a little bit more interesting than single variable, because we have to do a little bit more work to classify a point like this, because it will show up on both of those functions as being a critical point, even though it's really not a max or a min, because this is something called a saddle point. A saddle point is that Pringle shape. So remember, one of the ways that we could test if something is a maximum or a minimum was with something called the second derivative test. And the second derivative test basically said, if your function has a second derivative which is positive, which you can sort of think of concave up, looks like a happy face, then this critical point would be a minimum. You have a minimum if your, if your second derivative is positive and you have a happy face. If your second derivative is negative at a critical point, then you must be looking at a sad face, and that critical point must be a maximum. They're sort of creepy pictures, but I'm going to go with it anyway. So the second derivative test really helped us a lot to figure out, to sort of like classify these points as being a max or a min. And the problem is, with multivariable calculus, the second derivative test is much more complicated. What we use is something called the second partials test. And in order to use the second partials test, it's kind of like we combine these second partials in every way that we can. So we multiply the second partial taken with respect to x both times, so f sub xx, by the same thing with respect to y, f sub yy, and then we subtract from that the mixed partial squared. So in order to simplify this formula, I'm just going to write f sub xx, f sub yy, minus f sub xy squared. This is the second partial test, and it gives you some sort of like determinant kind of. Now, everything is friendly if the determinant here, I don't know if it's actually called the determinant, I just call it that, if that is greater than 0. So as long as this formula is greater than 0, then everything is normal. Then that means everything is normal. And what I mean by that is, then if your second derivative just with respect to x is positive, then it's kind of like you're looking at a concave up function, and you have a relative min. If your second derivative, your second partial, is negative, you would be thinking of concave down, and you have a relative max. So all of this stuff corresponds to single variable calculus, on the condition that this little determinant is positive in both cases. Now, if your determinant is negative, in any case, doesn't matter what your second partials are, if this determinant thing is negative, then you have a saddle point, and that's that Pringle shape. So what that means, I didn't write it on here in this section, but that is neither a max nor a min. And if the determinant is 0, then this test doesn't really tell you anything. So basically, friendly, friendly, saddle point, and then inconclusive. So as long as this little determinant is positive, then you can sort of go back to single variable and know the stuff that you already know. So let's use that. Here is a pretty friendly function of two variables, f of x and y. Now, in order to find the critical points, we just need to set both of the partials equal to 0 and find what are the points that make that happen. So I'm going to find the partial with respect to x, which is going to be what? 6x minus 2y minus 8. And I need to set that equal to 0. And I'm going to just solve this for y, like sort of solve it as like a normal kind of equation. Actually, I'm not going to do that yet. I'm going to wait. Then I'm going to find the partial with respect to y, which is going to be negative 2x plus 2y. Oh, I'm sorry, there's no 8 here on this first one. this derivative with respect to x is just 0. So this is just 6x minus 2y, and I'm going to set that equal to 0. This one is negative 2x plus 2y minus 8, and I'm going to set that equal to 0. This is going to give me a system. Now let me reorganize this a little bit. 6x minus 2y equals 0, and then negative 2x plus 2y equals 8. Here's my system of equations. Now first of all, I'm going to divide everything to make these a little bit simpler. So I'm going to rewrite my system as 3x minus y equals 0 and negative x plus y equals 4. And then I'm just going to use elimination and add those things together, and I get 2x equals 4, and so I find x equals 2. And when I get x equals 2, I'm just going to substitute that back into the very first equation, and I get 6 minus y equals 0, and so y must equal 6. So my solution to this system is the point 2, 6, and this is my critical point. So I found, and maybe there were going to be, on some other functions there could be more than one, but this function only has one critical point. My critical point is the point 2, 6. Now, this does not tell me whether this point is a maximum or a minimum, or maybe it's neither one. Maybe it's a saddle point, I don't know. So I have to kind of keep going and use some other tests. Now I can't just take a second derivative, I have to basically take all of the second derivatives. So I'm going to go back to my original function, and I'm going to find this determinant thing. So that is the second derivative taken both with respect to x, both with respect to y, and then the mixture x and y squared. So when I find the second derivative taken with respect to x both times, it's the derivative of this guy with respect to x, which is just 6. And then the derivative of this guy with respect to y, which is just 2. And then the mixed one, so I'm going to do this function and differentiate it with respect to y, which is negative 2. And then I'm going to square that. So for my determinant, I'm actually getting 12 minus 4, which is 8, which is positive. Now, as long as this determinant is positive, that tells me that everything is friendly, and I can basically go back to single variable calculus. And single variable calculus tells me as long as my second derivative is positive, then I've got a happy face, and as long as my second derivative is negative, then I've got a sad face. So it's just going back to concavity. Well, in this case, my second derivative, f sub xx, is positive, so I know I've got a happy face situation. My function is concave up, which means that critical point, that point 2, 6, must be a minimum, because it's at the bottom of a happy face. So this point 2, 6 is a minimum. And I've classified my, actually what I should say here is it's a relative minimum. It's a relative minimum. Now I don't have like I don't have a restricted domain here. And if I did have a restricted domain, I might have to test endpoints or corners or something. But in this case, everything we're going to deal with has an infinite domain. So I found the only critical point, and I classified it, and it's a relative minimum. So let's do it again. Now this function, also multivariable, so I'm going to start by finding critical points. And then I'll have to do some more work to classify them. But first I just have to find them. Find the critical points. So I'm going to find my first partials. The partial with respect to x of this one is 4y minus 4x to the third. And I'm going to set that equal to 0. And then I'm going to do the partial with respect to y, which is 4x minus 4y to the third. and I'm going to set that equal to 0. And this sort of gives me a system of equations. I can simplify these a little bit just by dividing everything by 4, and I can say y minus x to the third equals 0, and then also x minus y to the third equals 0, and now here's my system. So I have a couple of things that I can do. Elimination doesn't solve this one, so I might resort to something like maybe substitution. So I'm going to say I'm going to solve this very first equation and rewrite it as y equals x to the third. And then everywhere I see a y in the second equation, I'm going to substitute this in. So this is going to become x minus, and then everywhere I see a y, I'm going to put x to the third. So that's going to be x to the third to the third. And this equals 0, which gives me x minus x to the ninth equals 0, which is not great, but I can factor out an x, and then I get 1 minus x to the 8th equals 0, which gives me two values. So first of all, x equals 0 makes this quantity equals 0 and kills off the whole thing. And then also x equals, actually, sorry, 3 values, plus or minus 1 kills off this second quantity and makes the whole thing equal to 0. So I have 3 values so far, and now I just have to find their corresponding y values, because of course critical points in this setting means an ordered pair. So let's start a list here. When x equals 0, I'm going to plug that in to my original, actually I'll just plug it in here. When x equals 0, y also has to be 0 in order to solve these equations. So one of my critical points is 0, 0. Now, if I plug in x equals positive 1, I need to find the corresponding y. I'm going to plug it in here. X equals 1, so I'm going to get y minus 1 equals 0, so that gives me a y value of 1. So there's another critical point. And then if x equals negative 1, I'm going to plug that also in right here, and that would give me y minus negative 1 to the third equals 0, or in other words, y plus 1 equals 0. So y would have to be negative 1. And those are my 3 critical points of this function. Now, I don't know if these are maxima or minima, or if they're saddle points, or I just have no idea what's going on with these. So we need to do some other tests in order to classify these things, which brings us to the second derivative. So remember, the determinant of this thing, I don't know if it's called the determinant, is the second partial with respect to x both times, the second partial with respect to y both times, and then the mixed partial squared. So let's go back to our original partials. Here's the partial with respect to x, and I'm going to differentiate with respect to x again. So when I do that, I get negative 12x squared. And then the second partial with respect to y is negative 12y squared. And the mixed partial, so I'm going to differentiate this one with respect to y, is 4 squared. So let's simplify this. I get 144 x squared y squared minus 16. And I'm trying to figure out, is this greater than 0, less than 0, or equal to 0? So this is my determinant. And also, I mean, this only applies to each of these points individually. So let's evaluate first at the point 0, 0. So in this determinant, when I plug in 0, 0, I get negative 16, which is, that's like the weird situation. When the determinant is negative, that tells me this is a saddle point. So 0, 0 is a saddle point. That's the Pringle shape, neither a max nor a min. Let's try with 1, 1. Now at 1, 1, I get 144 minus 16, which is certainly positive. And that tells me that everything is friendly and I can go back to single variable calculus. So looking just at the second partial with respect to x. And at that value 1, 1, the second partial with respect to x is negative 12. So that tells me, thinking of single variable calculus and the second derivative, tells me I'm looking at a concave down function. And this point, then, this point 1, 1, must be a relative maximum. And one more. At negative 1, negative 1, that's going to be the same here. So the determinant is 144 minus 16, which is greater than 0. So everything is normal. And when I plug in negative 1, negative 1 into the second partial with respect to x, it's still negative 12. And so I have another relative max at negative 1, negative 1. So what I have, I guess I should classify these things sort of a little bit more formally. So let me write up an answer here. At 1, 1 and negative 1, negative 1, we have relative maxima. And the point 0, 0 is a saddle point. So neither a max nor a min, but it does say to classify saddle points in this example. So I'm classifying all of those, and I'm going to check my recording. Great. Okay. So that's how we use sort of the derivative stuff that we know to find maxima and minima of functions, and that brings us to, I think, just the last couple of exercises here. So starting on number 17, you're just doing that exact same thing. So first you're going to find the critical points. Using just the first partials. So set your first partial is equal to 0. And then you classify them by using that determinant with the second partials. And figure out if it's positive, then everything is friendly. And if it's negative, you've got a saddle point. And if it's 0, then it's inconclusive. But 17, 18, 19, and 20 are just doing that exact same thing. So finding the critical points and then classifying them. And if you have questions, come to our office hours this week.